Hey, welcome to Expressive DevCon 2024. My name is Morris. I'm working for Expressive as a software engineer in the chip support team. Many applications require unique interfaces that might necessitate sacrificing an SPI or UART controller. However, with just one channel, the RMT peripheral can drive your LED strip, D-short protocol motor, and even multiple one-wire bus temperature sensors. To achieve this, you need to create your own RMT encoder, which will guide the hardware in translating your application data into RMT symbols. In this talk, we will focus on the ways to construct an RMT encoder. Okay, let's get started. First, I will reintroduce the RMT peripheral by examining the IP block diagram. In this presentation, we will focus solely on the TX channel, as the RMT encoder is designed specifically for it. This includes how to allocate, configure, and send data using the RMT channel. Next, we will discuss how to construct your own RMT encoder. There are two types, Combinator and traditional callback function. Following that, we will explore some impressive examples implemented with different RMT encoders. Finally, we will address some limitations of the RMT hardware and how to mitigate them. And of course, your feedback is always valuable. From the block diagram, we can observe the followings. All channels share the FIFO RAM, which is divided into multiple blocks and can be accessed by either the CPU or DMA. All channels use the same clocks. For high resolution, select the PLL as a clock source. For low power consumption, choose the internal RC oscillator. The TX channel contains a counter. Set the divider based on the desired resolution. The output signal passes through the GPL matrix to the I/O pad. You can even modulate a high-frequency carrier onto the output. Next, we will see how to translate these hardware features into driver APIs. RMT hardware has significantly evolved since its first generation. For instance, channel 0 can function as RX on ESP32, but on ESP32S3, it can only be configured as TX. This inconsistency complicates writing a code that works across all ESP targets. Therefore, our driver does not allow you to designate a channel number. Instead, it searches for an available channel based on the requirements set in the driver configuration. Yes, this is the so-called factory design pattern. First, we select a clock source for the channel. If you want to install more channels, ensure they are set to the same clock. Otherwise, the driver will return an error. If the clock source is not a concern, just use the default one. Next, set the channel's resolution, which is the tick rate of the internal counter. A higher resolution results in a more accurate timing. Crucial parameter that should be set according to your application requirements in implementing the RMT encoder. Then choose a GPL number for the channel. The GPL number is the output pin of the channel. You can select any GPL number, but ensure it is not used by the peripheral. Set the size of the memory block used by the channel. A larger value means fewer interruptions to the CPU, providing more stability in environments with high interrupt latency. Set the transaction queue size, which determines how many transactions can be pending in the background. Finally, configure additional flags for finer control of the channel, such as leveraging the DMA functionality. Now, we can allocate the channel object, and the driver should return a handle. Please note, there is a key config option called config RMT ISR IRun safe. If enabled, the RMT driver can also operate when the flash cache is disabled. For example, when you're saving some data into the MVS state partition, with this key config, the driver will always allocate the channel object from the internal RAM. The driver includes a state machine, so you must call the driver API in a specific order. This reduces the risk of putting the RMT hardware into an undefined state. For example, calling RMT enable before starting a transaction, because it enables essential system services like interrupts, DMA, power management. Here, if you call disable first, then enable again, the driver can cancel the current transaction and start a new one from the queue. The transmit function is the front end where you prepare the data buffer and set transaction-specific configurations. You can specify the number of times to repeatedly transmit the same user data. Be cautious with the value -1, as it signifies an infinite hardware transmit loop. You can also set the idle level, which refers to the state when no transaction is in progress. The transmit function is non-blocking. It constructs a transaction descriptor and pushes it to a transaction queue, then returns. The real job will only start working once all previous transactions are completed. If an infinite transaction is in progress, the only way to stop it is by calling RMT disable. We've covered all the basic APIs you need to know, from allocating a TX channel to starting a transmission. What is an encoder here? How do I create an encoder from scratch? In the encoder driver, we use a design pattern known as a composite pattern. This pattern allows us to reuse the existing RMT encoder as a combinator. By chaining these combinators, we can create a new encoder. The public interface defines two crucial methods, the encode and the reset. The encode method is a core algorithm where the logic to pass user data into RMT symbols is defined. An RMT symbol is a 32-bit integer that represents the duration of a specific logic level. Let's dive into the encode method. The primary data here is the raw data provided by the user, such as the channel number of a TV. The encode function must correctly return an encoding state, indicating whether the current encoding section is complete and if the underlying FIFO memory has free space. This function is often called from an ISR. It's also recommended to play IRAM to achieve high performance and reduce interrupt latency caused by cache miss. Please don't spend too much time in the encode function, as it runs in an ISR environment, and prolonged execution may lead to an interrupt watchdog timeout. The RMT driver includes some native encoders that simplify the construction of a more complex encoder. Let's explore these further. The first type is the copy encoder. As the name suggests, it transfers data from the user to the hardware file in a ping-pong manner. This encoder does not perform any format conversion. The user data must be an array of RMT symbols. Here is the code snippet to create a copy encoder. You might wonder, when should copy encoder be used? The answer is straightforward. It is suitable for any scenario requiring encoded data. It can be used for a leading code in NEC protocols. Next, let's delve into the concept of bytes encoder. To create a bytes encoder, follow these steps. Define the representation of bit 0 in the RMT symbol format. Similarly, define the representation for bit 1. Decide whether to transmit the most significant bit or least significant bit. Finally, obtain the encoder handle by calling the create function. Now, when should you use a bytes encoder? If you have a byte stream to send and are aware of the utilizing the byter allows you to convert the data bytes into a RMT symbol stream. A core use case is converting an RGB buffer into RMT. Now that we have both the copy encoder and the byte encoder, create a more sophisticated encoder. Explore the general steps involved in designing RMT encoder for driving an LED strip. Begin by defining a struct type specifically for the LED strip encoder. The encoder should inherit an interface that we discussed in the previous slide. Additionally, we aim to reuse the bytes encoder and the copy encoder. The bytes encoder handles encoding RGB data, while the copy encoder will translate the reset code. We store the reset code in the struct for convenience. Since we cannot encode all data in a single step, we will need a variable to track the current encoding progress. Next, let's provide a factory function to create an encoder and its handle. We call a help function to allocate the memory for the encoder. Configures the bytes encoder to align with the bit definition of the LED strip. Construct the coder and create the RMT symbol that serves as the reset code. Don't overlook the implementation of essential methods for the RMT encoder. There are 3, with the encode method being the most critical. We will dive into it in the next slide. Find the encoder handle to the user. In accordance with the LED strip protocol, during each refresh cycle, we need to transmit RGB data for all LEDs, followed by a reset code. Now, let's dive into how this sequence is implemented within the encode method. Keep in mind that the LED encoder inherits the base RMT encoder interface. Therefore, at the outset of our encode method, we perform a polymorphism to convert the base RMT encoder instance into an LED strip encoder instance. Once we have the LED strip encoder instance, we can retrieve the bytes encoder and the copy encoder from it, both of which we created during the pre-allocation function in the last slide. The crux of the encode function lies in designing a state machine. For the LED strip, The state-machine transition is straightforward. First, transmit the RGB data, and then set the reset code. In the switch case, the branch corresponding to case 0 handles the encoding of the RGB data. It simply invokes the encode method that's provided by the byte encoder. The encode method is responsible for reporting the current encoding progress. Therefore, we check the value of the returned session. If it indicates that encoding is complete, we proceed to the next state. However, if the byte encoder yields due to insufficient space in the underlying FIFO, it must also yield. It's critical to propagate the encoding state back to the caller. Additionally, we have another switch case branch that performs a similar task, encoding the LED strip reset time using the copy encoder. Finally, upon returning from the encode function, we provide information about the current encoding progress and the number of RMT symbols generated. Combining the copy encoder and the byte encoder doesn't necessarily allow us to create all types of custom encoders. Instead, we have another native encoder called the simple callback encoder. As the name suggests, writing an RMT encoder becomes as straightforward as creating a callback function. The key to allocating a simple encoder lies in specifying the callback function. When examining the callback function closely, you will notice that it has a parameter list similar to the encode method. However, there is a crucial difference. Now, you also need to manage memory size. User can fine-tune the encoding process with greater granularity, but this comes with increased responsibility for memory safety. Let's write the encode callback function for the LED strip again. At the beginning of the callback, we typically perform parameter check to ensure that the remaining memory size can handle the task. Next, we translate RGB data into RMT symbols and write them to the symbol stream. In the previous slides, this step was handled by the copy encoder or byte encoder, but now you will need to handle it by yourself. Finally, don't forget to translate the reset code. How to choose between combinators and callbacks? There are trade-offs between these two programming paradigms. Combinators provide a straightforward way to compose functions. It encourages modular design, allowing you to reuse existing building blocks efficiently. Callbacks offer fine-grained control. Developers can manage execution flow at a granular level, which is essential for certain scenarios. Callbacks give you direct access to underlying mechanisms, but this can be more error-prone. Handling callbacks correctly requires careful attention to avoid pitfalls. Generally speaking, the combinators are well suited for complex encoding tasks where composition and abstractions are critical. The callbacks are ideal for simpler encoding needs, especially when precise control is necessary. By the way, the callback encoder is still integrated within the RMT encoder architecture. You can even chain the callback encoder with other native encoders. Beyond the previously introduced LED strip, we can utilize RMT for various other applications. The D-short protocol interface for ESC. This includes a D-short protocol encoder and leverages RMT's hardware loop function, enabling the driving of a brushless motor with minimal CPU utilization. the open-loop precision control of stepper motor. In this application, we construct an RMT encoder that generates precise PWM pulses, adhering to the S-curve characteristics for smooth start and stop of the step motor. The one-wire temperature sensor, unlike implementing using GPIO bit banding, the RMT-based one-wire bus can operate stably in an RTOS environment. It's unaffected by context switching. All hardware has its limitations, and RMT is no exception. During the development of the RMT encoder, we might encounter this issue. Why does the RMT transmit more data than expected? The root cause is the hardware transmitter reads from the memory before the encoder updating it. If the RMT encoding process spends too much time or is delayed by latency, the transmitter that are outdated. The issue is hard to eliminate because we can't command the transmit to pause and wait during one transaction. But this issue can be mitigated by employing the following strategies. We can increase the memory block size. We can place the encode function in the IRAM. We can use the DMA feature, or we can even install the RMT driver on a different CPU core. Thank you for joining us on this exploration of RMT. This presentation is the surface. May it ignite your curiosity and inspire further development. Feel free to share your experience in writing the RMT encoder on our ESP32 forum. And don't hesitate to report issues on our GitHub. I wish you also enjoy other topics in the DevCon 2024. Thank you for watching. Bye.